Hello, welcome to Chapter 7, Sampling Distribution of Sample Proportions, Confidence Intervals. In Chapter 6, we worked with the binomial distribution and with the normal distribution, and we saw that the binomial can be approximated with the normal when the number of trials is big. In Chapter 1, we introduced the concept of parameter, which is a characteristic in a population, and the concept of a statistic, which is a characteristic in a sample. Usually we cannot observe the parameter because the population is too big. All we can observe is the statistic in one particular sample. In this Chapter 7, we will study how important the normal model is to draw a conclusion about the parameter based in the observed value of the statistic. In other words, we are beginning the last part of our journey, which is inferential statistics. That's to say, speaking of the population in the light of our sample. Let's comment about this title. Sampling distribution means what happens with certain statistic as we pick more samples. The statistic we work with in this chapter is the proportion. Let's see this with an example. We have a population of college students in which the proportion of female students is 60%. From this population, we pick many simple random samples, all of them of size 100. Letter A. Each sample may show a different proportion of females, but what pattern will we see as we continue to pick samples like that? To answer this question, I usually do a dramatization of a simulation with my students. I tell one of them, imagine that you have access to all the students. 60% of them are women. Now you randomly pick a sample of 100. You have the sample in front of you. How many women do you have there? And the student says 62. Okay, 62 in a sample of 100 is a proportion of 0.62. I do the same with another student. You pick a new sample. How many women do you envision in this sample? 55. So a proportion of 0.55. Another student, pick a sample. How many women do you imagine? 30. This means a proportion of 0.30. The last student, pick a new sample of size 100 and count the number of women in that sample. How many? 70. Proportion 0.70. Now I graph these four proportions in a dot plot. The first, 0.62, the second, 0.55, the third, 0.30, and the fourth, 0.70. Here are some simple questions. Are all these proportions possible? Students always answer yes here, and the answer is yes. Are they equally likely? Here I usually have some students who answer yes. They say, since the individuals are selected randomly, any sample is as likely as any other. The answer is wrong, but the reasoning is interesting. Let's say that in this college there are 3,000 students. 3,000 choose 100 is the total number of possible samples of size 100. Any of these samples is as likely as any other. The student was right about that. But it is also true that some proportions are more likely than others. The reason is that in this sample space, to use the vocabulary introduced in Chapter 5, very few samples will contain only 30 women. To the contrary, many samples will contain 62 women. That's why we can say that the proportion 0.62 is much more likely than the proportion 0.30. Then the answer here is no, not all the proportions are equally likely. Among those four, the most likely is 0.62, and the least likely is 0.30. In simple terms, a simple random sample tends to be representative of the population. We studied this in Chapter 1. Since the population proportion is 60%, the sample proportion will tend to be around 60%. The farther away, the more unlikely. If you have understood this, you can answer question A. What pattern will we see as we continue to pick samples like that? We will see that many sample proportions fall in 0.60 or around 0.60, and fewer fall farther and farther. In other words, the sampling distribution of sample proportions will fluctuate around 0.60 with an approximately normal shape and a standard deviation of 0.049. Where do we get this standard deviation from? I don't think you can understand this just with intuition, but you can understand it with a bit of algebra. Picking a random sample from a population is essentially a binomial situation. The number of trials is the sample size, and the probability of success is the proportion in the population. We saw in the previous chapter that for a binomial model, the standard deviation of the number of successes is the square root of this. The point is that now we don't work with the number of successes, but with the proportion of success. How do we turn this into the standard deviation of the proportion of successes? Simple, we divide the number of successes by the amount of trials, that's to say, the sample size, n. Now, applying basic algebra, this n enters the root squared, and with basic algebra again, these two get cancelled. So here we have the formula for the standard deviation of the sampling distribution of sample proportions. P is the parameter proportion in the population, 0.60. This is its complement, 1 minus p. N is the sample size, 100. When you do this, you get 0.049. Here you have the final conclusion. The sampling distribution of sample proportions follows approximately a normal model with a mean that equals the proportion in the population and a standard deviation that equals this. This is the mathematical model that you must know, remember, and be able to use. Before finishing this part, which is the theory, I have 3 comments. First, for this model to be a good approximation, the sample needs to meet certain conditions, usually called normal conditions. It must be random, it must be reasonably big, this means that it must have room for on average 10 or more failures and on average 10 or more successes. And it must be reasonably small. Usually we say that it must be less than 1/10 of the population. Second comment, the standard deviation of a sampling distribution is commonly called a standard error, because it is the average error of the statistic compared to the parameter. It's the average distance between the proportion in the sample and the proportion in the population. We will denote it as E. Third comment, if you do the average of these 4 proportions, here I have it, you will see that it does not equal 0.60. Why? Didn't we say that the mean of the sample proportions equals the proportion in the population? Yes, what happens is that here we don't have all the samples, we have only 4. The total amount of possible samples is population size choose 100. This is an astronomical amount. If we could get the proportion in each of these samples and average them all, we would get 0.60. We cannot do that, but what we can do is, with simulation, picking 400 or 4,000 or 40,000 random samples. The more we get, the closer the average of their proportions is from 0.60. This is again the law of the large numbers, which we studied in the previous chapter. Let's practice what we have learned with letter B. If we pick one more sample of size 100, what's the probability that this sample shows a proportion of women greater than 65%? We can answer this question with the binomial distribution, with no need for any normal approximation. In fact, we solved an analogous exercise in the previous handout in chapter 6. This is a binomial situation with 100 trials and a probability of success of 0.60. The only minor limitation is that the binomial model does not work with the proportion, but with the number of successes. But we can turn the proportion into a number easily. In a sample of 100, a proportion greater than 65% means more than 65 successes. If you do this as we learned in chapter 6, you will get 0.130. Let's use now the normal approximation. First, we are under normal conditions. The sample is random, it's obviously less than 1/10 of the population, and in 100 students, the expected number of females is 60, which is more than 10, and the expected number of males is 40, which is also more than 10, so we are good to go. Then we know that the sampling distribution of sample proportions will follow approximately a normal model whose mean will be 0.60 and whose standard error will be this, which is approximately 0.049. We did this before. If the statistic follows this distribution, what's the probability of this statistic taking a value greater than 0.65? The normal calculator will tell you 0.154. Notice that these two probabilities are different. Is it because of the rounding? No, it's not an issue with the rounding. They are different because the binomial and the normal models are different in nature. The binomial is discrete and the normal is continuous. Therefore, their probability distributions are irremediably different. And then you should be wondering, which of these two probabilities is more accurate or better? I think this is better. As I explained in the previous chapter, when the sample is huge relative to the sample size, we can assume independence in the selection of the different individuals of the sample. And then we are in a perfectly binomial situation, of which the normal model gives mere approximations. Ironically, in this moment, we are more interested in having you do it with the normal approximation. Indeed, for questions like this, the normal model is more commonly used than the binomial. The main reason might be tradition. If you don't have a friendly software, as people didn't have 15 or 20 years ago, getting this probability is way easier than getting this. Here, you just need to get the C-score of this value, which you can do manually, and the table will give you the probability. Here you need to use a complex formula to get this probability, all the other ones up to the 100, and then you need to add them all. With modern softwares you can get this directly, it is faster and more accurate, but we still want you to learn how to use these normal approximations. Anyway, there is a benefit in knowing the standard error, and there is also a benefit in knowing the C-score. Let's practice the normal approximation with exercise 2. The proportion of defective pieces is 7%. We pick a simple random sample of 500 pieces. Letter A. What's the probability that the sample contains a proportion of 8% or more defective pieces? First, we check that we are under normal conditions. In a sample of 500, we are expecting 35 defective pieces, which is more than 10. And 465 non-defective pieces, which is also more than 10. The sample is random and obviously is very small compared to the population, so we are good to go. The sampling distribution of sample proportions will follow an approximately normal distribution with mean 0.07 and this standard error, the square root of the proportion of success times its complement all over the sample size. That's 0.011. And now the question is, what's the probability of one of those samples showing a proportion of 0.08 or greater? A normal calculator will tell you that this is 0.182. Letter B. What's the probability that the sample contains a proportion of 10% or more defective pieces? Using the same normal model, we put this in the normal calculator and we get a probability of 0.003. Letter C. What would you think if the picked sample contained a proportion of 10% or more defective pieces? As you see here, the proportion of such a thing is very small. On average, we would have to pick more than 300 samples before seeing one with a proportion of defective pieces of 10% or more. So here there are two options. Either a very unlikely type of sample was selected, or the proportion of defective pieces produced by the machine is indeed greater than 7%. If the proportion of defective pieces was, for instance, 9%, a sample like this would be very common. This dual answer is the basis of hypothesis testing. We work with this in the next chapter, chapter 8. The second part of this chapter 7 is dedicated to confidence intervals. Let's approach the concept with the help of exercise 3. We have a population of big size and a proportion P in this population. There is an enormous amount of samples of size n that we can select, all of them equally likely, and each of them has its own proportion, denoted p hat. If we were able to graph all this enormous amount of sample proportions, we would see that they fluctuate around the population proportion following a normal model with this standard error. According to the empirical rule studied in chapter 6, this means that 95% of all the possible samples of size n have their sample proportion between here and here. That's to say, within 2 standard errors from the population proportion. We can call them usual samples. 2.5% of all the possible samples of size n have their sample proportion here, and another 2.5% have their sample proportion here. We can call these unusual samples. Now we are going to do something. We are going to pick one of these samples randomly, and around its proportion we are going to open a perimeter or an umbrella or an interval of plus minus 2 standard errors. Notice that if we happen to select a sample whose proportion is, for instance, here, its umbrella will cover the parameter, that's to say, the proportion in the population. If the sample has a proportion here, its umbrella will still cover the population proportion. However, if the sample has a proportion here, the interval generated around the sample will not include the proportion in the population. In a case like this, the parameter is not contained in the interval. And the same is true for any sample whose proportion falls anywhere here or here. Neither of these samples will generate an interval that contains the parameter. If you understand the mechanic of this procedure, you are ready to answer letter A. What's the probability that the resultant interval contains the parameter P? The probability that an interval built that way contains the parameter P is approximately 0.95, because for 95% of all the possible samples, the interval built that way will contain the parameter P. A student once made a nice suggestion. He said, if we pick one of those unusual samples, what we can do is reject it and pick another one until we get a usual sample. In this way, we always get an interval that contains the population proportion. There are 2 reasons why this idea doesn't work. First, we usually cannot pick a second sample. Second, and most important, when you have your sample, you don't see the distribution of all the other millions of samples. All you see is something like this, and you cannot know if this sample is a usual one or if it is an unusual one, because you see the sample alone. All you know is that 95% of the times it will be usual, 5% of the times it will be unusual. This 95% is what we call the confidence level. The most common confidence levels are 90%, 95%, and 99%. Let's see how to apply these concepts with some exercises.